All right, hello everyone. Today we're moving on to section 8.2. In the first section 8.1, we took a look at some of the properties and theories that represent acids and bases. Now we're going to take a look at and identify the differences between strong and weak acids and bases before we start looking at the equilibria that are involved with acids and bases. So by definition, a strong acid is going to react very quickly and pretty much to completion. Okay, so it's going to ionize 100%. All right, is what is going to happen here. It will ionize 100%. So some good examples of strong acids are the following. We got hydrochloric acid, nitric acid, chloric, perchloric acid, hydroiodic acid, hydrobromic acid, and sulfuric acid. The rest of the acids are classified as weak. All right, so it's going to be important to know the difference because we're going to solve these problems very differently. All right, so by knowing which ones are strong acids and which ones are weak is going to be beneficial to you. All right, so taking a look, what do we mean by 100% ionization? All right, so when I place HCl, which is my acid, into water, notice what's taking place here. All right, what's going to happen for a strong acid is that as soon as I put the HCl in water, all of it's going to dissociate, leaving me with all of these white molecules here. Okay, all of these white molecules, which are my hydrogen ions in solution. This is pretty much 100% dissociation. Okay, as soon as it's put in water, it dissociates 100%. However, with the weak acid, you're only seeing about 10% is going to be dissociated. So what happens when we place a weak acid into water, only a few of those molecules will ionize into hydrogen ions and the anion, all right? And so the remainder of it is going to be still intact as the weak acids, all right? So that's generally the difference between a strong and weak acid. Now we can determine the strength of an acid and we can describe it in a variety of different ways. All right, by looking at the acid ionization constant Ka, it is going to be very large value for strong acids and is going to be quite small for weak acids. So that's a good indicator to help us in determining the strength of an acid. All right, it too is going to give us the position of the ionization equilibrium. So what it's going to tell us when we do have a strong acid, it is to the far right with respect to the reaction, while weak ones tend to be more to the left. Okay, and with respect to the hydrogen ion concentration, the concentration, so this is very important, my hydrogen ion concentration is equivalent to the initial concentration of the original acid at the start of the reaction. So they're equal in essence. For a weak acid, though, the concentration of hydrogen ions at equilibrium is going to be much less than what the initial concentration of the acid that we were looking at. All right, so these are very, very important properties and ways in which we can describe the strength of an acid. So if we recall, we can write the Ka from our previous section. If we use the general equation, it is represented by hydrogen ions concentration times the anion over the acid Ha, which is my general acid formula. Okay, and so this is going to represent it for a weak acid. However, the Ka for my strong acid is H plus ions and my anions. So this would represent it for my strong acid, and that's what we're going to be looking at today. All right, these represent my strong acids. All right, ones that ionize 100% in water. Now here are some examples of the Ka values, the acid ionization constant for some common acids. This is just a very shortened version of the table, but you'll notice that my strong acids here have very large Ka values, so they are not even included, but the strength of the acid increases as we go up. Okay, now a weak acid will only partially ionize in water. We usually say about 10%. All right, so usually the number here is 10%, is how much of it will be found in solution. All right, we're going to learn to look at these particular reactions in the next section in 8.4. So let's look at a typical question with respect to concentration of strong acids. All right, so this is an example of a strong acid. We want to find the hydrogen ion concentration, H3O plus 1, or the hydronium ion, in 250 milliliters of water, which contains 0.01 moles of hydrochloric acid. All right, so ideally, folks, we can set up our ice table to keep ourselves organized, just so that you know exactly what's taking place here. So we'll practice doing that. So I will just say we're going to set up an ice table, and we're going to let X represent the change. All right, so we have to start off with the equation here. We've got HCl, and it's being placed in water. And we're forming hydronium ion, or we can write H plus for short. But this way it sort of shows us where the hydrogen is being donated based on the Bronsted-Lowry theory of an acid and a base, and the HCl has lost it. So if we put our acronym ICE, okay, we know that we do not incorporate because it's a homogeneous reaction, we do not include H2O. And we know that at the start, the information that we've been given here, the 250 and the 0.01 moles, is the initial concentration of the HCl. So to find the initial concentration, I'm going to say the HCl, I'm going to call it little I for initial concentration, is going to be equal to the concentration formula. You're going to need to use that. C equals N over V. We're given the moles, which is 0.01 moles, and we're given the volume, but don't forget, when we use the molar concentration formula, our volume must be in liters. So I convert that to liters in my head, and it gives me 0.25 liters, which tells me that the initial concentration is 0.04 moles per liter, which is this concentration right here. Okay? Initially, on the onset, we do not have any hydronium ions, nor do we have any chlorine ions. Now, because this is a strong acid, it's ionizing 100%. So if I know the concentration of my initial HCl, that is going to represent the concentration of my HCl at equilibrium. Okay, so I don't have to do any initial calculations. So therefore, the concentration of H3O plus at equilibrium is equal to 0.04 moles per liter, because HCl is a strong acid and ionizes 100%. So in essence, you don't actually have to do a full ice table here. You would, as long as you have the understanding that because it's a strong acid, if I know the initial concentration of the acid, which is given in the question, it will represent the amount of hydrogen ions at equilibrium because of the 100% ionization. Very important concept to remember and know. Now, strong bases behave exactly the same way as strong acids. Okay, a strong base is going to occur quickly and go to completion as well. All right, so it's going to dissociate 100%. So for these ones, we are going to be using the symbol Kb. The symbol Kb represents the base ionization constant, okay, which is AKA the base dissociation constant. All right, so they mean the same thing. And because we're dealing with strong bases, Kb is going to equal the concentration of the ions and hydroxide ions for this particular question. So because it's a strong one, and you notice here that this is a heterogeneous reaction, this sodium hydroxide solid gets incorporated into my Kb constant. Okay, so the strong acids and strong bases are always going to go to completion. Weak bases are only going to partially react with water. Once again, it's only about 10% to produce these hydroxide ions. Okay, so we will talk a little bit more about them in the next lesson. Now, the ionization of pure water, another important concept, is called the auto-ionization of water. All right, so if we take water, notice what's happening here. This hydrogen is being given, so therefore this is acting as my acid, this water molecule, while this one is acting as the base. So we can simply rewrite this equation as follows. Water can ionize to hydrogen ions and hydroxide ions. Now this is important. It's at SATP, standard temperature, ambient temperature and pressure, if you recall from grade 11. And this is at 100 kilopascals and 25 degrees Celsius. So what we can come up with then is what we call Kw. All right, and so Kw then is the hydrogen ion concentration times the hydroxide ion concentration. And this is equal to 1 times 10 to the negative 14. All right, very important number to remember. This here is my ion product constant for water. At SATP. Okay, and so therefore from this relationship here we can determine the following. Okay, so if we were to replace this and want to find the concentration of hydrogen ions and the hydroxide ions, we let it define it as X. So X times X is going to equal 1.0 times 10 to the negative 14. So when I solve for X, it equals 1.0 times 10 to the negative 7. And this here, folks, represents the concentration of my hydrogen ions and my hydroxide ions. Okay, so this here is going to equal H plus ions and my hydroxide ions. Okay, that is my value of X. All right, that's how we define it. Okay, so this is going to be a very important relationship to remember. So therefore, we can summarize these relationships with respect to hydrogen ion concentration and hydroxide. In an acidic solution, the concentration of hydrogen ions is greater than 1 times 10 to the negative 7, while the hydroxide concentration is going to be less. So if we look at the relationship, we've got more H plus than we do OH. And hence the pH is going to be 7, less than 7. All right, so that's where that 7 comes from. My basic solution is the opposite. I'm going to have a greater concentration of hydroxide ions over hydrogen ions. Okay, hence that's where we get a greater value of pH greater than 7. And in a neutral solution, the two concentrations are equal to one another. Okay, and that gives us the neutral pH of 7. Now to the side here, we see what the pH scale is. All right, and how it relates to the hydrogen ion concentration. Okay, with neutral being 7. And notice that the concentration 1 times 10 to the negative 7 represents its exponent, okay, with respect to the concentration of hydrogen ions. So each one of these, as we go up, becomes more basic, and as we go down, it becomes more acidic. All right, so very important to see that relationship there. And lastly, some very important relationships that we've seen in this section. The first one here that you'll need to know, okay, is the relationship between our ion product constant Kw is their concentrations are equal to 1 times 10 to the negative 14. So from this equation here, we can derive the concentration of hydrogen ions is equal to Kw, which is 1 times 10 to the negative 14, over the concentration of OH. Or we can also find the hydroxide ion concentration if asked, and we would divide Kw, which is a given, as 1 times 10 to the negative 14, over my hydrogen ion concentration if I am given that particular concentration. So we can manipulate this relationship into two different equations. The next thing that we can look at are some of our pH relationships. This one here is my first one. pH is equal to the negative log of the hydrogen ion concentration. Likewise, if you're asked to determine the pOH, it's the negative log of the concentration of the hydroxide ions. All right, another important relationship, if I add up the pH plus the pOH, that equals 14, which is our pH scale. Okay, and lastly, we can also find the concentration of the hydrogen ions by taking the inverse, which is 10 to the negative pH. So if you're given the pH, you can determine the concentration of hydrogen ions. Likewise, if you're given the pOH, you can find the hydroxide ion concentration. And lastly, we can use KW is equal to the product of KA times KB. All right, all very simple formulas that we need to be able to use and recognize. Now, for homework, that is, I'm not going to go through all of how to use each of these equations because they're pretty straightforward with respect to just plugging in the numbers and then solving for them. So what we're going to have you do is read over section 8.2. This is especially important is to read over the sample problems before tackling these homework questions. Okay, and there is a typo there. It's questions 1 to 3 here, folks. Okay, so very, very important that you first read the sample, then try those questions that follow it. Okay, so each tutorial gives you some sample problems to look at, then try the homework questions. It will be very easy for you to do, so good luck, and we will see you in the next lesson.